To begin with, let's look at some of these properties. We basically have b and c are real numbers, n is a positive integer, and then we have these functions f and g, and they have these properties. The limit as x approaches c of f of x is going to equal L, whatever that is, and this limit over here with g of x at the same x value will be approaching k, and we have all of these properties. So basically, if we have some number multiplied by a function, then the limit is just going to be multiplied by that same number. And that should make sense because the limit is basically the height of the function. So if f of x has a height of L, and then we multiply that height by b, it would make sense that the limit's height would also multiply by the same value. Sum or difference, basically same idea. If we have two limits that are being added together like this, if we have the limit of two functions being added or subtracted apart, we can actually just separate it out and evaluate the limit of each one separately and then add or subtract the answers together. Same thing, if we have the limit of multiplication, we can basically evaluate each limit separate, so the limit of f and the limit of g, and then multiply those answers. Same property holds true with division, as well as raising things to powers. All right, so for these examples here where we're just simplifying using those properties of limits, we have a limit as x approaches 3 of f of x equals 7, same x approaches 3, but for g of x equals 12. So here the properties limits say that we can basically evaluate each one of these separately. So we can do the limit as x approaches 3 of f of x, it's going to be 7. The limit of as x approaches 3 of g of x is 12. So we just do 7 minus 12, and that's negative 5. So we're done. Same idea over here when we have multiplication, we just do 7 times 12, that's going to be 84. Ta-da! Here we will have g, so that's going to be 12 to the 1/2 power, so that's really the square root of 12, which we could simplify all the way down to 2 rad 3 if we really wanted to. And here we'll have 4 times f of x, so that's 4 times 7, and that's going to be 28. Ta-da! Properties of limits. Make it really easy, just separate things out. All right, we got a flashback to chapter 2. We're going to analyze this rational function, and then we're going to try to see if we can write a whole bunch of limits for it. Super exciting. So I have this up here, x squared minus 1 over x minus 3. First thing I'm going to do is factor everything, top and bottom. That's just to make sure we don't have any holes. For the x-intercepts, that's when we set the numerator equal to 0. So I'm going to get plus or minus 1 comma 0. And I'll just come over here and plot those points here and make my red marker no longer red. Super. For the y-intercept, I'll let x equal 0, so we're going to get negative 1 over negative 3, so that's going to be a positive 1/3, so I'll just estimate that as around there. Vertical asymptote, that's when we set the denominator equal to 0. I will get x equals 3, so I'll just come over here and draw that vertical asymptote here, and I'll note that it has a multiplicity of 1. End behavior asymptote. So we have different rules here. When the degree is bigger on top, that means that we need to divide. So I'm just going to do a super quick division here. So I want x squared, I only have an x, I need to multiply by an x. So I'll get x squared minus 3x. And then I'll get 3x minus 1. I need a 3x, I only have an x, so I'm going to do plus 3. Don't need to do any more because everything else after this would be a remainder, which would drop. So I get y equals x plus 3. So that's going to be way up here, and I didn't give myself enough room on the graph for us to actually see what we're going to need to do next. But we always look for a place that is above or below the x-axis as a starting point, so the y-intercept tends to be a good place. I know that I have to intersect these 2 points. Doesn't matter which way we go. I'm going to cross here because it's an odd multiplicity, and then I have to follow this asymptote as it goes out. Here I have to get close to this asymptote. I can't go above this axis because there's no x-intercepts. Odd multiplicity says I'm going to bounce up here, and then I need to follow that. So there's like this weird little check mark up there. I'm not sure if you can actually see that on the screen. I'll pull it down just in case. So now that we have that, let's look at a bunch of the limits that we can talk about here. Okay? So first, let's do the limit as x is approaching negative infinity of this function, and the limit as, I'm going to try to straighten this out, there we go, as x approaches positive infinity of f of x. So as x is approaching negative infinity, that's talking about the end behaviors here. So this graph is going down towards negative infinity, and as we're going that way, it's going up towards positive infinity. So whenever x is approaching positive or negative infinity, this stuff is talking about the end behavior asymptotes of the graph. Now there are a couple other ones that we could look at, particularly right here at as x is approaching 3. So let's do limit as x approaches 3 from the left, and the limit as x approaches 3 from the right, and then we'll have the actual limit as x approaches 3 of f of x. So as we approach from the left, it's going down, so this is going to be negative infinity. As we approach from the right, it's going up, that's positive infinity. Those are not the same number, so the actual limit does not exist. So here we have when x is approaching numbers and y is approaching infinity, so the limit is approaching infinity, that's going to indicate the presence of vertical asymptotes. So for this one, we always try direct substitution first. Right, that's always our first move. So direct substitution gives me 0 on the bottom. It does not give me 0 on top, and that's what's going to tell me that we have a vertical asymptote. So officially, vertical asymptotes are when we get a number over 0. And there's a couple different ways we can evaluate it. I'm going to stick to just us graphing. Next year in calculus, you'll learn some other potential ways that you could evaluate these ones. So if I graph this stuff, I'm just going to do a super quick graph, nothing fancy. I'm going to have a vertical asymptote over here with a multiplicity of 4. So that multiplicity of 4 is important. That means I know it's either both going up or it's both going down. So let's try to graph this stuff here. My end behavior is going to be at 0, so I know that it's right here. And if I try to factor that, I'm not sure if it factors to anything. So I'm just going to do the inside of the quadratic formula to see what happens. So I'm going to get b squared minus 4ac. So this is going to be a negative number, which means that there are no real solutions. So I'm never actually intersecting this line ever. So I'm either always above it or always below it. So next I will look for the y-intercept. So when x equals 0, I'm going to get 10 over 3 to the 4th. That's a positive number. That's all I care about. That's enough. So I now know that I have to be up here. There's nowhere for me to cross. Even multiplicity, I'm going to stay up here, and again, nowhere for me to cross. So this is asking, what is the limit as x approaches 3? Well, it's going to be infinity because both of these are going up. Okay, so I'm going to try to direct substitute, and when I do this, I end up with 0 over 0, which actually indicates that there might be a hole here. So I'm going to actually try to factor. So I'm going to get 5x minus 2, and then on the bottom I will get x minus 2 squared. So this is going to reduce to 5 over x minus 2. Guess I don't need that extra parenthesis there. So if I try direct substitute, I now get 5 over a number. So this actually is a vertical asymptote at x equals 2. And I have a end behavior asymptote at 0. I have no x-intercepts because 5 doesn't equal 0. The y-intercept is going to be at negative 2.5, so it's going to be right here. So I now have enough to do a quick sketch of this. This is asking the limit as we approach 2. From the left, it's going down towards negative infinity. From the right, it's going up towards positive infinity. Those are not the same number, so this limit does not exist, as Lindsay Lohan told us in Mean Girls. So I'm going to try to direct substitute into this, and even though we're approaching from the left-hand side only, we can still try to direct substitute. If direct substitution works, then the left-hand and right-hand limits are equal to the real limit. But if I plug in 1, I get 1 minus 2 plus 1, that's 0 on the bottom. So I'm going to try to factor to see if this will actually help me out. Either way, it helps me graph it. So I can pull out a 3x squared. I'd be left with x minus 1, and on bottom, I'm x minus 1 squared. So things do actually cancel. It makes my life a little bit easier when it comes to the graphing stage. I still can't direct substitute though because I will get 3 over 0. But I can graph this super quick. I'm going to have an x-intercept at 0 with an even multiplicity, so I'm bouncing off of that one. I'm going to have a vertical asymptote at 1 and an end behavior asymptote of approximately 3x. I'm just guessing here. I don't actually know what it is, but the reason I'm not figuring it out is because we don't really care. They're not asking us about what's happening at the end. And I just did 3x squared over x to get approximately 3x. That actually gave us enough to know that this is coming from here. It's going to bounce because of the even multiplicity x squared. Odd multiplicity asymptote, so it's going to go like this. So I have a rough idea of the graph. This is asking me just the left-hand side of 1, which is going down towards negative infinity. Okay, for limits at infinity, we're going to do something a little bit strange. There's a couple different ways you could solve these ones. This is my preferred method. I think it's way easier to do it this way, but basically I'm going to pretend like it's perfectly fine for me to plug in infinity for x. So I'm going to direct substitute in infinity. So I'll have 5 plus 2 times infinity over 3 minus infinity. And then I'm going to just evaluate the top and the bottom separately from each other and then compare top to bottom. So if I have 5 plus 2 times infinity, I like to think of this in terms of money. If I have $5 and over here I have $2 billion, do I really care about that extra $5 that I got from someone? Or I'm just like, no, I'm rich, I got $2 billion. So essentially I can ignore this 5 because it doesn't mean a whole lot compared to 2 billion. Same thing down here. If I have minus $1 billion and I pay someone $3, I still pretty much owe them $1 billion. So I can ignore that 3, but not the negative. So what I really have is 2 infinity over negative infinity. And now I can cancel out the infinities and I'd be left with a negative 2. So that's what this limit is approaching. Do the same exact idea here. I'm going to evaluate, this is negative infinity, I wrote it down wrong. So I'll have negative infinity plus 4. On the bottom, I will have negative infinity squared minus 2 times negative infinity plus 5. Evaluating just the top, if I owe someone $1 billion and I pay them $4, I pretty much still owe them $1 billion. Here we get a little bit trickier with things going on here. So I think we know that the 5 is going to drop, but what about here? This is really infinity squared plus infinity. So I'm just going to write out a really big number here. So here's, let's see, what is this? That's 1 million. This is going to be 1 billion. Let's actually just do it with a billion. If I square 1 billion, that's going to give me, instead of 9 zeros, I'll have 18. Whew, that'll be way over here. So basically, if I have whatever ginormous number this is, okay, and I add this, it only changes the number right here. So essentially, this is really small and I don't care about it either. So on the bottom, I really just have infinity squared. Now when I cancel, I'll have negative 1 over infinity. And what happens when we have a really big number on bottom? This whole thing is approaching 0. So this limit is going to be 0. Okay, here we have x approaching negative infinity. I will again just direct substitute that in. So I get negative infinity to the third minus 4 times negative infinity plus 5 all over 4 minus 2 times negative infinity squared is what I believe that said. So when I'm doing this stuff, essentially these don't matter. Same thing with this 4. So I have a negative infinity to the third over a negative 2 infinity squared. So the infinity squared is going to cancel out with all of those. So I'll have negative infinity over negative 2. And the negative signs cancel. And half of infinity is totally just infinity, which is crazy, but that's what happens. All right, for these ones, we can see the title is varying end behavior. So that means we're probably going to get different answers when we plug in positive infinity versus negative infinity. So let's start off here. If we do the limit as x approaches positive infinity, we'll get 5 infinity to the third minus infinity over the square root of infinity to the sixth plus infinity. So we got to try to simplify this stuff down. On top, I basically just have 5 infinity to the third. I don't really care about that minus infinity. On the bottom, I'm going to focus just on the inside first. And this infinity to the sixth is basically way bigger than the infinity, so I can ignore that. Now I just need to simplify this. So if I have the square root of infinity to the sixth, that's really infinity to the third. Those cancel. This is going to equal 5. Now if I do this exact same thing as x is approaching negative infinity, let's see how that changes things. When I plug in this up top, we'll have 5 times negative infinity to the third. It'll be plus infinity. And then in the bottom, I'll have negative infinity to the sixth minus infinity. So up top, I get a negative 5 infinity to the third. The plus infinity goes away. On bottom, the square root is still there. We have negative infinity to the sixth is going to become positive infinity to the sixth, and we don't care about the minus infinity, so I really just have infinity to the sixth. So simplifying that a little bit more, the square root of infinity to the sixth is infinity to the third. Those cancel, and I'm left with negative 5. So this thing is going towards 5 on one side and negative 5 on the other side. Kind of neat. This one is math teachers' favorites. You'll see this a lot in calculus. So as I do the limit as x approaches positive infinity, so I'll just plug this in, 4 minus 5 to the infinite power over 5 to the infinite power minus 3. So this 4 doesn't mean a whole lot, so I really just have minus 5 to the infinite power, and 5 to the infinite power minus 3 doesn't mean a whole lot. So those cancel, and I'm left with negative 1. That wasn't so bad. For the limit as x approaches negative infinity, when we do this, we'll get 4 minus 5 to the negative infinite power over 5 to the negative infinite power minus 3. And here's where things start getting a little bit trickier. So this 5 to the negative power, well, that's really 4 minus 1 over 5 to the infinite power. And it's really important. It only flips around itself and not across the large fraction. So what is 1 over 5 to the infinite power? Well, that's basically 0. So we end up getting 4 minus 0 over 0 minus 3. So this one is negative 4/3. So next we have some limits for trig functions, and what you should do is actually graph this in your calculator. Graph sine x over x and just look at it as we get closer to 0, and you'll see that this is approaching 1, and same thing if we do x over sine x. If you were to graph 1 minus cosine x over x, it's approaching 0, and if we flip that, we end up getting one that does not exist. So these are all ones that you should memorize, particularly these top two ones, that sine x over x equals 1 and 1 minus cosine x over x equals 0. When x is approaching 0, they're different values if x was approaching something else. Okay, so what we're going to do for these examples is basically first try to direct substitute. If we can't do that, then we will try to look for these different patterns up here. So if I try to direct substitute, I will get 0 over 0, so that's not going to work. So the next thing I'll do is separate this. So I'm going to pull the 7/3 out. The tangent, remember tangent's really sine over cosine, so when I write this, I'm going to write this as sine over cosine. So I'm actually separating the tangent into that. I'm going to put the x right there, and I'll put a 1 up here. So if we multiply all of this, we really have 7 sine over cosine, so tangent, over 3x. And I will evaluate each one of these separately. So limits of constants are constants, so that's 7/3. Limit of sine x over x as x approaches 0 is going to be 1. We just learned that up there. And 1 over cosine of 0, that's 1 over 1. So this is going to be 1 over 1. So this is going to equal 7/3 for that limit right there. Over here, we'll try direct substitution. We would get 3 times 0 over 4 minus 0. Okay, that works. 0 over 4 is in fact 0. So we didn't need the properties. We could just direct substitute and it worked perfectly fine. Here, we end up getting 0 over 0, I believe. So I'm going to separate this out just like we did up here. So I'm going to pull the constant out first, so 1 and a 2. And I'm going to factor the sine out of the top as well. So I'll have sine x. I'll put that one over x. And I'm left with a 1 minus cosine x. Kind of running out of room here, but... and so it doesn't really matter. We could put the x here, we'd end up getting 0. We could actually put it here. So I'm going to put it there just so that we can experiment with this a little bit more. So I'll get limit of 1/2 is always going to be 1/2. The limit as sine x of 0, that's going to be sine of 0 is 0. And 1 minus cosine x over x is also 0. So this is going to be 0. So no matter what, we end up with 0. Here, try to direct substitute doesn't work. So what I'm going to do is separate the fraction because I have a single thing on bottom. So I will end up with something like this. This reduces to just x minus 3 times sine x over x. The limit as x approaches 0 of x is going to be 0 minus 3 times 1. Sine x over x is approaching 1 as x approaches 0. So this is going to be negative 3. Done. All right, for piecewise functions, what we basically need to do is figure out which which part of the piecewise function we're going to be looking at as we approach each one of these. So what I like to do is label each interval as A, B, and C, and then I come down here and try to figure out where is this x value. So x values of negative 3 are going to fall in A's interval. So I'm just going to put a little A here. 0 from the left is in A. 0 from the right is in B. And since this one is different, I just won't bother putting one. In fact, let's just not put one for any of them other than the lefts and the rights. 3 is firmly in B, so I'll have B and B. 5 from the left is in B, but from the right is in C. 9 is firmly in C. So now that I've done this, I just have to pay attention to which one of the 3 different equations I'm looking at. So first thing I'm going to do for A is this can be factored and simplified. It simplifies down to 2 over x minus 3. So I'm going to first see, can I direct substitute? So if I plug in negative 3 into that equation, I will get 2 over negative 6, which is negative 1/3. And since direct substitution worked, that's the answer for all 3 of these ones then. I'm not going to box them anymore. I don't know why I did that. Now, for x approaches 0, from the left, we'll use this equation. I plug in 0, I'm going to get a negative 2/3. Now, as I approach from the right-hand side, I'm using this equation now, okay? So if I plug in 0 for this, I get 2 over negative 3. And since these are the same number, that is what the actual limit equals. As I approach 3 from the left, well, that's a vertical asymptote here, right? So I'm just going to do a quick graph of this. Here's 3. It has end behavior at 1, x-intercept at negative 2, y-intercept at a negative 2/3. So I end up with something that looks like that. So since I have that, I can very easily see that this is negative infinity, this is positive infinity. That means that the real limit does not exist because they're not the same. For 5, from the left-hand side, I'll plug it in right here. So I will get 7 over 2. So that's what this one will be. When I'm looking at it from the right-hand side, I'm going to be using this equation. So I will just plug in 5. That's going to be 15 plus 1. So that's going to be 4. Since these are not the same number, the limit does not exist. When I plug in 9, I'm going to get some crazy number like 28, which can simplify down to 2 rad 7. Since direct substitution worked, these are all 2 rad 7. So to summarize piecewise, we basically first figure out where the x value is that we're approaching, which one of the pieces in the piecewise it's doing, and then we just go back and do everything that we've already learned. Finally got to the practice 8 million years later.